All right, section 3.5, we started this last time. We're looking at trigonometric equations, and the ones that we did last time were kind of challenging. Just as a reminder of what we've done, there are some basic strategies for solving these equations. Deciding if the equation is linear or quadratic. If there's only one trig function present, then we simply solve for that trig function. If more than one is present, we rearrange things so that it's zeros on one side and everything else is on the other side. Try to factor and then to solve, which is also what we do when it's quadratic, is that we put everything on one side, factor and solve. We haven't done that yet. We'll do one of those, or maybe a couple, I can't remember. And then sometimes, number 4, it's necessary to use some trig identities to change things so that you're able to do any one of these other features, okay? And we'll see some of that today as well. So the examples we had done, this is one where it just had a plain old trig function in it. There's not two of them. There's not squared, nothing like that. And we were able to take a look at a unit circle perspective to figure out where in the world this actually happened. And then we were able to find out that this was this one was when we were evaluating it. I apologize. I was ahead of myself. I'm on the next slide already in my head. This is one where we put the number in, the evaluation in, and for the angle, and we checked to make sure that it worked. It did, and we were good to go. This is the one that I was at in my head, where we simplified and solved for just sine x, moved it to the other side. We talked about paying attention to the directions. If the directions say all, that means something. A lot of the directions are not going to say all. You're just going to have a couple of them that will. But when it says all, you're going to have this extra language here at the end where we add 2 pi times k to things, and k is an integer. And it gives us that rotation where it keeps going around and around the circle, giving us all of the rest of the potential values that we would have that would solve the equation. After that, this was the same variety. This one was a little weird, I should mention, because it had a triple angle. And so we weren't able to just find that one place. We were having to find all of the values that worked from here and here and here. And so we did it 3 times because we had a triple angle. And this one has directions that are mistaken. I was like, I feel like that's not quite right. On your paper, it actually said, not all here, it actually said on the interval 0 to 2 pi. So we did it right. The directions are just messed up at the top. This is what it says in your notes, okay? So we did it on the interval for 2 pi. We did 3 of them because it was a triple angle. If it had been 5 of them, we would have done 5 of them because it would have been a 5 times the angle, right? So the fact that we did this 3 times, that's my highlighting and or marking anyway in green underneath, was because there was 3 inside with that angle. And here we are. So we're taking a look now. And again, I think it's because I copy pasted too much. None of these are supposed to be all, so they should say, good grief, to do from 0 to 2 pi. Yep, all of them are wrong, but that's okay. We can fix that quick. Okay, we'll do it for those 2. I'll make a change it as we go. Okay, so we're finding the solutions between 0 and 2 pi. And we do have just a plain old cosine. The only difference with this one is that the angle inside's a half angle. Now we have some half angle formulas, and you can make use of those if you'd like. But there's really not a need to do so because we can do this directly just like we did with our triple angle last time. But it's easier because I don't have 3 times I have to do it. It's a half angle, which actually sometimes means I have fewer answers than I would have had otherwise. So let's take a look. This one wants us to find places first where the cosine is equal to 0. So if you're thinking unit circle, where on the unit circle is the cosine equal to 0? Remember, cosine is x, pi over 2, and 3 pi over 2. Is that good for everyone? Okay, so we're going to say that this happens at the angle, which our angle is theta over 2, at pi over 2, and at 3 pi over 2. Okay. We're not going to divide by 2. We're actually going to multiply. So our goal is to get theta alone, right? We want to solve this for theta. And so right now that theta is being divided by 2, so we're going to multiply by 2. And we're going to simply do that to every value that we have here. So if I take, of course these cancel, which was the point, but if I take pi over 2 and I multiply it by 2, what do I get? Pi. And 3 pi over 2 times 2 would be 3 pi.
so you don't write it.
Yeah. So this list would go on, right? We could continue this list, but remember the goal is to do it on the interval we were given. And I've written it on the top, but it's actually written in properly on your notes. It's supposed to be just the answers between 0 and 2 pi. So if you get extra answers, that's okay. You just need to recognize that the answer to the question then is actually going to just be that theta is equal to pi because it's the only one that's on the interval I was asked to find. Does that make sense? This one is outside of 0 to 2 pi. So it's not a solution based on the question's directions. Okay, everybody good? So I mentioned that specifically because, so if you did this on the test or on a quiz, I'd just take a point off or half a point off or something like that because you didn't pay attention to directions. If you do this in my math lab, it's just going to tell you error, red X, right? And you need to go back and pay attention. Why did it do that? This is a really easy thing to forget if you're moving too quickly to check that step at the end. So check that if you're getting an error in my math lab as being wrong and you're pretty sure that you did it right, you might be outside of your interval. Okay, let's take another one. Take a look at another one. Okay, so this is a tangent value. Again, very similar to the ones that we had looked at on the last couple of them, last 3 of them actually. But it has more than just the angle inside. So it doesn't have a 3 times the angle. It doesn't have half of an angle. It's got a shift, right? We talked about this when we did our phase shifts with graphing. It's shifted somehow. So the process starts out the same though. This is asking us where we have tangent values that are equal to 1, okay? So thinking unit circle, where do you have tangent values that are equal to 1? Okay, so they're 45-degree angles. They're either tangents are 1 or negative 1. So in quadrant 1, we always have positive values. What other quadrant do we get? Which one? Yeah. So there's another quadrant here where I'm going to have a tangent value that's going to be positive. And it is quadrant 3. And remember before, too, we did this last time, a smart trig class. Tangent is positive in quadrant 3. So we have the angle right here at pi over 4. What's the angle all the way around over here? Okay, so it's our angle, theta over 2 plus pi over 3. It's pi over 4. And then I'm going to write a separate one. You can write it to the side. I've got more space to write it underneath, so I will. Oops, it was over 3. And it's 5 pi over 4. Okay, is everybody good on where the pi over 4 and the 5 pi over 4 came from? You remember tangent values are sines over cosines. They're places where the x's and the y's have the same value. Those happen at 45-degree marks. We want to make sure we're getting the positive ones in this case. That's in quadrants 1 and 3. So it's pi over 4 and 5 pi over 4. At this point, both of these can be solved using typical algebra kind of techniques. If you want to eliminate the denominators first, you can. If you want to just isolate the theta part over here on the side first, you can. We have a couple of options. So what would you guys like to do first? We'll solve one of them, and then we'll have the same process to solve the other one. So you want to subtract pi over 3? Is that okay with everyone? Okay. So we're going to move the pi over 3 to the other side. So that leaves me with theta over 2 on the left. And then what do I have to do in order to subtract these?
Get a common denominator.
You guys agree? I have to have a common denominator. What will the denominator that's in common be? 12. So I'm going to multiply the first one by 3 and the second one by 4. And if I do that, I'm going to jot this to the side so that we can have it all there. This is 3 pi over 12 minus 4 pi over 12. And what is 3 pi over 12 minus 4 pi over 12? Yep, negative pi over 12. So now I'm at negative pi over 12. What am I going to have to do to solve for theta then? Multiply by 2. This is like our last problem, right? Then we're going to multiply by 2. Now, this theta then is equal to negative pi over 6, which is not exactly what we want. Well, it doesn't not matter. We're going to have to fix it. We're going to have to fix it. This angle, negative pi over 6, is an angle that goes around one time. It's just going the wrong way. Are y'all with me? So I'm going to need to figure out what that negative pi over 6 should be if I went around the right way, right? The clockwise, the counterclockwise way instead of clockwise. So I'm going to come back to that in just a second. Let's just solve the two equations right now because they solve similarly. So if I do the same thing over here and I do minus my pi over 3, and I get a common denominator. Whoa, 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 whoa. That one's a 4 there. And then there's my 3 and my 3. So this is 15 pi over 3 minus 4 pi over, 3. What do we get when we subtract here?
I wrote the wrong number, but
15 and 4.
11 pi over 12.
We need 11 pi over 12. Yeah. Oops, I've written them on the wrong number. Sorry, moving too fast. Those are 12s. Okay, it's 11 pi over 12. So we have theta over 2, and it's 11 pi over 12. And just like the last one, we're going to multiply by 2, right? So my theta, wow, it's not working very well, is it? My theta is 11 pi over 6. Now pause for a minute to consider what this actually is if we were going the right direction instead of, in this case, sort of the wrong direction. So if we went this way, we'd have negative pi over 6, right?
It's the same thing, the same spot.
It will be. So if we go this way around instead, it will be 11 pi over 6. So it actually ends up giving me the same thing I already have down here. That doesn't always happen. I want you to recognize that that's unique in this particular one. That is not an always thing.
So if it was like negative pi over 4, then it would be 7 pi over 4.
Right.
Okay.
So it just depends on the angles you're working with. The reason it's happening is because I have a theta over 2. I mean, that's why it's happening here. I recognize that. But in general, we need to pay attention to the fact that if we were to take this value and we were to add 2 pi to it, which is essentially what we did by going around the other direction of the circle, we might not actually end up in the same place that the other answer gave us. So we could still have 2 answers on this. We don't just get to discard it completely. Okay? You might be asking, well, how did I know that I could discard the 3 pi completely? Well, it's actually kind of the same reason. I didn't mention it, but maybe I should have. If you went 3 pi around the circle, where would you be? You'd be the same place you would be for pi, right? So if we were to sort of reset 3 pi to its location in a one-time around the circle business, it'd be already the other answer we already had. Okay, so our only answer on this one ends up being 11 pi over 6. Okay, any questions? Okay, so let's, all of those problems had kind of the same feel to them. I had one trig function, I looked at a unit circle, and then I figured out, based on whatever the angle inside was, how something got manipulated. They really are all the same. They're different because the process is different because of what's inside, but the initial starting point of those problems is very similar. I look at a unit circle and I figure out where I am, at what angle I'm working at. We're going to shift gears for the next one, and it is going to be different. So on the next one, we actually have something that's squared, right? This is like that first thing on the list of like things to consider, strategies, pay attention to, whatever you want to call them from the very first slide. This one's not linear. It's quadratic. So when things are quadratic, we need everything on the same side, which is kind of nice. This one's already all on the same side. But shifting something to the other side works when it's linear. That's all the last problems I'm doing. This one's not. I need it all to stay on the same side. And what I'm going to end up doing is I'm going to end up factoring, but I want to sort of remind you of what this would look like in its analogous situation if we were doing things in algebra. If this were an algebra problem, this would look like x squared plus 2x plus 1. Okay, so right now, this cosine x business is acting like a variable plain old x in terms of the structure of this equation. I've got something squared, I have 2 times that same something, and then I have a constant on the end. Okay, can you see the parallel in the picture? So if I were working with this problem that I've sort of recreated over here, and we wanted to factor, we'd say, okay, well, I need an x and an x to get an x squared, right? I'd say, oh, look, there's a 1 on the end. I need a 1 and a 1, otherwise I can't multiply and get 1. And I would say, oh, look, that 1 on the end is positive, so my signs need to be the same. And the sign in the middle is also positive, so my signs need to be positive. And I would check to make sure that when I did the inner and the outer terms, that they would actually add to 2 in the middle. So this is a 1x, this is a 1x. We add them together, we get 2x, and they check out. Okay, that's how factoring works. If factoring is a place that you struggle, you probably need to brush up on that a little bit because it's going to come into play in this section. Now let's go back to our original problem and see that it works the same way. In the original problem, I don't have x squared, I have cosine that's being squared. So at the beginning, I will have the cosine of x in each of my first pieces of my factors. The end is still a 1. I have to have a 1 and a 1, otherwise I won't multiply them together and get a 1. The sign at the end is positive, which means my signs have to match. The sign in the middle is positive, which means they match and they're positives. And if I check the inner and the outer terms, this is 1 cosine x and 1 cosine x, and what happens when I add them? 2 cosine x, which is what I want. Yep, Isaiah.
Why is this not right? Why can't we just do this?
You're going to get answers that don't work.
Okay.
Yep. All right. We can look at it more a little bit later if you'd like, Isaiah, and we can see what answers you get. But okay, is everybody okay with this so far? The factoring looks different, but it's actually quite similar in the way it comes into being. Okay, I'm going to erase the green parts here so I have more space to work. What we do next then is we have what's called the zero property of multiplication. It says if these two things multiply together to be 0, one of them had to be 0 to start with. Now they happen to be the same thing. That's not always going to happen. So in general, you're going to have two things that are multiplied and you're going to set each one of them equal to 0 and you're going to solve each one of them. Here they're the same, so I only need to do it one time. This is cosine of x plus 1 is equal to 0. But at this point, this problem looks like the last 4 or whatever it was that we've done. It's a linear equation. So now I will move the 1 to the other side. And I will look at the unit circle. And on the unit circle, where is the cosine value equal to -1?
Probably
Probably at pi. Do we agree? It is at pi, right? Cosine is the x value. The x value is -1 if we're at pi. So over to here, pi is what we're looking at. And that's the only time if I go around the circle one time. This is supposed to say the top on the interval 0 to pi, 2 pi, excuse me. So if I go around the circle one time, this is the only time I'm going to get x equal -1. So this is going to happen when the x value is equal to pi, and there's nothing else to solve. So while it's quadratic, which requires a little bit more work on the front end, right, we have to factor it and so forth. On the back end, what you tend to see with these problems is plain old x or theta or alpha or whatever inside, which means once you look at the unit circle, you're done. There's no more manipulating, dividing by 2, multiplying by 2, adding and subtracting. None of that tends to happen on these problems. The focus is on the factoring part of it at the beginning. Are you with me? So we only have one answer to this particular one. Again, typically we would have more than one, maybe even up to 4. In some cases we would have 4. Oh, okay, you ready for another one? Okay, not only does this one have squareds, it also has sines and cosines, correct? Now, there's more than one way to do this problem, but the truth is it's very nicely structured exactly like it is. I have two things, they're both multiplied and they're equal to 0. That's the exact situation that I worked to get this one into. Two things, both multiplied, set equal to 0. Okay? So just because you see something that's squared, just because you have a Pythagorean identity, just because you have power reducing formulas doesn't mean you have to use them. Okay? This problem is really nice the way it already is set up. Because the 0 property of multiplication says since these two things are multiplied and equal to 0, I can set each one of them equal to 0. And I can solve them. So I have the sine squared of x is equal to 0. And I have the cosine squared of x is equal to 0. Now, if this did not say equal 0, I can't do this. If this said equal to 1, I'd have to move the 1 to the other side. I'd probably need to change something using a Pythagorean identity or power reducing or something like that. It's because this is equal to 0 that I can do this. But that's actually also very friendly here because what happens if I'm trying to solve sine squared of x is equal to 0? What would be your first step? What's that?
So you just need to pump up x to 0, or you could take the square root if you really.
Okay, so we're going to take the square root because in general, if I see something that's squared equal to something else like this, I will want to take a square root. But what Isaiah is recognizing is that the square root of 0 is what? 0. So this is just the sine of x is equal to 0. And I can do the same thing over here for cosine. So the cosine of x is equal to 0. Okay, unit circle. Thinking about sines and cosines. Are you starting to understand why we needed that unit circle to be memorized so well? It keeps coming back up over and over again, right? Everything we do seems to sort of hinge back on it. Where is the sine value equal to 0? Yeah, so you said 2 pi, I think, Becca, and you're right, but we want to go only around the circle one time this way. So it'd be 0. That would be that one. And where else? And at pi. Because the 0 and pi give me this one. So this one is at the x values of 0 and pi. Where's the cosine equal to 0?
It's pi over 2 and 3 pi over 2.
Yep. Pi over 2 and 3 pi over 2. And all of those are between 0 and 2 pi, right? We've written them all in the right form for it to be between 0 and 2 pi, which is what the directions are supposed to say in the top here. All of my directions are going to be messed up on this. Now, my math lab might have you put them in order from smallest to largest. It kind of likes to do that sometimes. So if it wanted you to do that, like, I don't care on your test. It's a completely irrelevant thing. It has to do with the programming of the system. Like, that's why they might have you do that. It would look like this, right? So if you need to put them in order from smallest to largest, you can think about just going around in your unit circle and hitting all of my yellow and green dots in order, and that will work too. All right. So far, the primary thing that we haven't done, I'm going to go back to this list of ideas. The primary thing we haven't done is number 4. We haven't used any trig identities to change the form of the equation, right? We haven't done that. That's going to change with our next problem. We are going to do that on our next problem. So our next one, directions should still say 0 to 2 pi. Gives us an equation that has angles that are different. So when you have angles that don't match, that's kind of a red flag that says, I got to get the angles to match. If the angles don't match, I can't do the problem very well. Now, if you'd had angles not matching here, it would have been okay because you could have still set each of them equal to 0. You could have still solved each of them. That would have been fine. But over here, there's addition and subtraction with the different angles. And that makes the problem challenging as it's currently stated. But we do have a whole bunch of identities. And the identity that we're going to want to use is going to be to change this piece right here. The other piece we know how to work with. We've done things with that. We need to change the cosine of 2 theta into something that's more convenient to work with. So grab your identity sheet out if you don't already have it out. And I want you to take a look at finding an expression that I can change cosine of 2 theta into. Did you find a place where it's got cosine 2 theta written? Yeah? Did you find 3 formulas you could change it into? Yeah. This is a place where you have to use sort of some strategic thinking. They're not all equally usable. I need one that's going to be usable for my situation. Any idea, looking at the 3 that are there, which one is most usable? The second one has cosine squared only in it, and that is the one we want to use. So why would I want to change this? I'll write it in here so you can see what it looks like. Why would I want to use that formula as opposed to something that had sine in it? Because the cosine on the other side is already part of the problem. Are you with me? So when you look at these, you have to sometimes make a decision. And there are decisions that will work and there are decisions that will not work. Okay? This one will work because it matches the rest of the problem and allows us to continue the problem. So if you make a decision and you find yourself stuck later, you might go back to that decision and reevaluate whether or not that one was a good choice. All right? And then change it if it's not. Okay, so here at this point now, we have this. And I have something squared, right? And Isaiah's right. This becomes a problem where I want it all on one side because I have a quadratic. Quadratics mean I need everything on the same side in order to be able to solve them. So I'm going to shift everything. I'm actually going to shift everything over here to the right-hand side because having my squared term positive is usually easier for factoring purposes. So I'm going to choose to move my cosine of theta to the left. So I'm going to subtract a cosine of theta. And I'm going to choose to add my 1, which is actually kind of friendly because the plus 1s are going to go away, right? That's not all bad. So these two add to 0. So on the left-hand side, I have 0. On the right-hand side, I have 2 cosine of theta squared minus the cosine of theta. There we go. Okay, so we've got a squared, and it's not the only thing there. It's not just like cosine squared equals a number. So at this point, I go back to factoring. What is common to both of these? Because I don't have 3 pieces, right? On the last one that I did factoring on, I had 3 pieces. It was a trinomial. I had to work with all 3 of those pieces. I only have 2. So looking for a common factor is our approach. What is the factor that is common to both of these terms? The cosine of theta. And if I take a cosine of theta out of a 2 cosine of theta, the 2 stays, and one of the cosines stay as well. Here's the place that people tend to make a mistake on this problem, or a problem like this, is that they close the parenthesis and they think they've finished. But I need to take the cosine of theta out of this cosine of theta as well, and when I take it out, it doesn't become 0. It becomes 1, and it has to be negative because there's a negative between. Remember, factoring is like division where you can still see what you divided by. If I factor out the cosine of theta, it's like dividing it. And dividing cosine of theta by cosine of theta gives me 1. All right, this again ends up having 2 pieces that I can set equal to 0. Okay, 0 property of multiplication. So I'm looking for cosine of theta to equal 0, and I'm looking for 2 cosine of theta minus 1 to equal 0. One of them is already almost solved, right? Cosine theta equals 0 is almost done for us, so that's the one we're going to start with. And we're thinking, again, unit circle. On the unit circle, where's the cosine equal to 0? It's pi over 2 and 3 pi over 2. So this is my angle. It's at pi over 2 and 3 pi over 2. Half of the problem, half my solutions anyway, are found. What am I going to have to do with this piece? Add a 1 and then divide by my 2. So I'm going to move the 1 first. This is 2 cosine of theta equals 1. And then if I divide by 2, I have the cosine of theta equals 1/2. Okay, I've done a lot with zeros now in my unit circle, but not a lot with 1/2s. Where does cosine equal 1/2? Okay, so up here in quadrant 1 at pi over 3. And let's pause for a second to make sure everybody can think through this. What other quadrant would I need to be for a cosine value that's positive? Olivia? Yeah, it's 4. Sorry, that's a V, IV, down here at 4. So it would be measured at the same pi over 3 angle down here. And that angle down here is 5 pi over 3. So over here, my thetas are at pi over 3 and 5 pi over 3. And again, you could be asked to put them in a increasing order or something like that. But we'll just call it good at that point on this problem for our purposes. Okay, is that okay? So we ended up getting 4 answers out of a quadratic this time. Okay, the next problem is our hardest one, I think. Number 9. Let's see what's after 9. Let's see if that's true or not. Yeah, I think this one's the worst. 10's kind of messy too, but this one's the worst. I think this one's the worst because there's square roots of 3's involved. That makes it look really scary, maybe, or a little bit messy at the very least. And we have trig functions that don't match as well. Do you see that? I've got a tangent theta on one side and I've got a cotangent of theta on the other side, and they're related to one another, but they're not particularly simple to just use a formula and change in a very nice way. I mean, we're going to have to use a formula and we are going to change it. It's just not quite as friendly as the last one we did. So how are tangent and cotangent related? They're reciprocals, right? They're flips of each other, okay? So we're going to take one of them and turn it into the other one, and kind of the natural choice is to leave the tangent. Sine, cosine, and tangent get top billing all the time, and so we're going to take our cotangent and we're going to turn it into a tangent. So the left-hand side is going to stay the same, tangent of theta plus 1. The right-hand side is still going to have a square root of 3, and it's still going to have a square root of 3 here, but then cotangent is going to be 1 over tangent. Okay, is everybody all right with that step? Okay. We don't like trig functions in denominators, though. That's not an especially friendly way to have it written. So while you backtracked, you were right, Isaiah. We do want to multiply by that tangent theta. But you have to do it to every piece of the problem. I'm missing one, so let me put it in here. I realize I have a benefit. Some of you are working on your iPads too, have a benefit of shifting some things around. But the tangent theta has to be multiplied by everything. So on the left, this gives me tangent squared of theta. And then I have a tangent of theta. On the right, I have a square root 3 tangent theta. And then what do I have? I just have a square root of 3. So these cancel out, which was the whole point, really. Okay. I now have a quadratic. When I have a quadratic, what do I have to do? Yes, I need everything on the same side. Are you all tracking on that okay? So even if at some point we get stuck on this problem and we can't figure out what to do with that radical 3, at this point you still know I've got a quadratic, and with a quadratic, everything has to be on the same side. All right? So let's move everything to the same side. Again, I like my quadratics, the x squared terms or the squared terms, to be positive. So I want to move everything to the left-hand side this time because tangent squared is already positive over there. So we're going to shift this. I've got a tangent squared theta, and I've got a tangent theta. And then I'm going to move the square root 3's. So it'll be negative square root 3 tangent theta to move it to the left, and a negative square root 3 to the left equals 0. We've seen a number of different factoring things today. We've seen factoring with trinomials, right? You have 3 terms and you factored into 2 separate pieces. We've seen factoring where we just pulled out a common factor. This is another factoring technique. It's called factoring by grouping. I have 4 terms, and when you have 4 terms, factoring by grouping is the approach to go with. So what you do is you group them together in pieces that are sort of similar, and they're kind of spaced that way already. If you take a look at the first 2, they have something in common. And if you take a look at the second pair, they also have something in common. And that's going to make things work nicely. So tangent squared of theta and tangent of theta have what in common? Tangent of theta. And if I take that out, I'm going to be left with a tangent theta and a 1, right? Not 0, 1. What do the next 2 have in common? The square root of 3, and it's negative, so I'm going to pull out the negative square root of 3, which is going to leave me with a tangent theta. And then what happens when I divide negative square root of 3 by negative square root of 3? What do you have, Brielle? You're telling me it. It's 1, right? When you divide something by itself, you get 1. Now, that's a really good thing. Look at what's in those parentheses. What do you see? The same thing, right? They match. That's kind of the hinging point of factoring by grouping, is that when you group them, you have something that matches within those groups. So those 2 pieces get pulled out in front, like I'm factoring the piece that's in parentheses out now. So the tangent of theta plus 1 gets factored in front. And the pieces that remain get factored and put together afterwards. So tangent theta and minus square root 3. And now we have 2 sets of parentheses being multiplied, right? The stuff inside, and it equals 0. So we have that multiplication property of 0, where all of this is equal to 0, and we set all of this equal to 0. All right, I need to shrink this a little bit, so some more space. If we take the tangent of theta plus 1 equal to 0, what will I do next? Subtract the 1, so this is tangent of theta is negative 1. Okay, unit circle. Where is tangent negative? Just negative for now. Which quadrants? 2 and 4. So I'm going to be here, and I'm going to be here. And what are the angle measures that give me a tangent that's 1?
Probably 3 pi over 4.
Yeah, just 1. Because remember, in order for tangent to be equal to 1, it means sine and cosine are the same, or x and y are the same. It always happens at the pi over 4 angles. So they're at these angles right here, the pi over 4 angles. What is the pi over 4 angle in quadrant 2?
3 pi over 4.
It is 3 pi over 4. And what is the pi over 4 angle in quadrant 4?
7.
It is 7 pi over 4. This is 2 of my answers. All right, the other one I think is harder. Its tangent of theta is equal to minus the square root of 3 equals 0. So tangent of theta is equal to square root of 3. So remember, this is the sine over the cosine that's going to equal square root 3 over 1. And the location where that happens is when that's square root of 3 over 2 and 1/2. So this is equivalent to asking, where is the sine of theta equal to square root 3 over 2? Now, it's still giving me negative values, right? This one's giving me positive values. I apologize. This is square root of 3. So I'm supposed to be in quadrants 1 and 3 now, right? 1 and 3. So in quadrant 1, where is the sine value equal to square root 3 over 2?
Pi over 3.
It is pi over 3. So the angle is at pi over 3. And in quadrant 3, where is the sine value equal to square root 3 over 2? I know it's negative, but that's okay because it's going to cancel with the negative on the cosine. But where is it a square root 3 over 2 value? So we're up here like this. It's also got to be at a pi over 3 value down here like this. So this is pi over 3. What is the over 3 value down here? Yeah, it is 4 pi over 3, correct. So the other one over here is at 4 pi over 3. So I feel like this one is a hard one to do for so many reasons. And one of it here at the end is simply that we don't process tangents as well as we process sines and cosines. So if it helps you to change something in a sine and cosine to give you some perspective on your unit circle, then please do that. Okay. Last problem that requires us to do everything by hand. This one's finding all the solutions, not all though, but it's on the interval 0 to 2 pi. What part about this looks different than the ones we've done in the other problems? We've had parentheses. I don't think that's it.
6 and 4 theta.
Yeah, the angles don't match, right? We've kind of looked at that before. The angles don't match, but both of them actually don't give you just theta. They're both giving you something different. If you take a look at your trig identity sheet, do you see one that talks about taking two sine values and subtracting them? Yeah, it's actually a sum to product because we've got a sum, and this is a difference right here, sum or difference, a difference right here. And it's the second one on your list, and it does like this. It says we're going to do 2 cosine of some angles and then sine of some angles. And in all of those formulas, the first parenthesis is the angles added and divided by 2. And the second one is the angles subtracted and divided by 2. So the first one is angles added. So this is 4 theta plus 6 theta over 2. And the other one is 4 theta minus 6 theta over 2. So if I add them together and divide by 2, what is the angle that I get? I get 5 theta. Okay. The other one then, sorry, just checking that. And then the other one is 4 theta minus 6 theta divided by 2. And what's that one going to give me? That one's a negative theta. Negative inside of sine. Sine is an odd function, which means the negative inside is equivalent to a negative outside. So I'm going to change that. I'm going to rewrite this as negative 2, cosine of 5 theta, sine of theta equals 0. Do you see the multiplication property of 0 again? Two things being multiplied, set equal to 0. All of this can be grouped together if you'd like, and all of this equals 0. So this is negative 2 cosine of 5 theta equals 0. And this is sine of theta is equal to 0. All right. The sine of theta equals 0. The second one's the easy one. Let's just do that one first. Where does sine of theta equal 0? 0 and pi. Everybody good with that? That's the easy one. Any idea why I say the first one's harder? Okay, but what part about it makes it harder? It's not the negative 2, it's the 5. So negative 2 is easy because I'm just going to divide by negative 2, it's just going to go away, right? If I divide by negative 2, this is just going to say cosine 5 theta is equal to 0. So the negative 2 doesn't affect us, but the 5 theta does. And it affects us in the very same way that it affected us on the problem that we ended with last time. It means I have to go around the circle 5 times. Okay? Now, where does the cosine of theta equal 0? Just cosine of itself. Yeah, pi over 2 and 3 pi over 2. Okay? So, this 5 theta is going to be equal to pi over 2 and 3 pi over 2. That's fine, but that's going around the circle 1 time, right? What's the next one if I go around a second time? Next pair. 5 pi and 7 pi. They're all odds.
Does not go outside the...
It does, but when we divide it by 5 in a minute, it won't. I know, that's why we're going to do it 5 times. Ultimately, we have to divide by 5, right? That's why we're going around 5 times, is because when we divide by 5, it's going to reset it, and we're going to be back inside of the 0 to 2 pi. So 5 pi and 7 pi, what would be next? 9 pi and 11 pi. What's next? 13 pi and 15 pi. What's next? We got one more set. 17 pi and 19 pi. And they're all over 2s, right? So there's our last set. And we're going to divide every single one of them by 5, which is the same as multiplying by 1 over 5. All those denominators will become what? 10. 5 times 2, 10. So instead of getting pi over 2, I'm going to get pi over 10. And I'm going to get 3 pi over 10. And I'm going to get 5 pi over 10, which we'll reduce in a second. 7 pi over 10. 9 pi over 10. 11 pi over 10, 13 pi over 10, 15 pi over 10. How far did we go up? 19. 17 pi over 10 and 19 pi over 10. And this one reduces to pi over 2. And this one reduces to 3 pi over 2. All right, so here's what I'm going to do. I'm going to push pause. I'm going to let you guys head on out, and I won't push pause. I'm going to end the recording. We have 2 problems left. They're probably about a total of a 4 to 5 minute lecture, and they use the calculator, okay? So I'm going to record a third video for this section. It'll have that last 5-ish minutes on there for you to watch and to be able to look at. It's actually not that different than something we've already done. We actually did it back in chapter 1. So it's really almost like a review piece as well, okay? So I'm going to stop this one, and then we will record a second one later, or third one later.